Hello and welcome students. Welcome to this video lecture. This is Mohammad Awesh from Shri General Mission PG College, Lucknow, and I am thankful to Dr. Meeta Saji and who is head of the department of JNMPG College Physics, and also I am grateful to Professor S.D. Sharma sir. Both of them motivated me to develop this e-content for students. So thanks to them. Now my topic of discussion is Gibbs paradox. Okay, so before discussing this, let me tell you what is the Cambridge Dictionary meaning of this term paradox is. Okay, so according to that dictionary, paradox is a situation or a statement that seems impossible or is difficult to understand because it contains two opposite facts or characteristics. Okay, so according to that dictionary, any self-contradictory statement is a paradox. Okay, so where does this Gibbs paradox come from? Let us see that. Okay, so to understand that paradox in statistical mechanics, let us consider the three cases as I have shown there. Now, case 1, you can see that in case 1, what I want to show you is that there is a container, okay, this one, and that container has a partition. Okay, that partition divides this container into two equal halves. Okay, and I can remove this partition when required, when or as required. So in first case, there are some gas molecules just in the left portion of this container. Okay, just only in the left portion of the container. So the volume available to these molecules is half of the volume of the total container. Okay, now when I remove this partition, okay, then obviously this gas will undergo this Joule expansion. Okay, and the whole of the gas molecules will diffuse and will spread in the throughout volume which is available now. Okay, so since this Joule expansion is a irreversible process. Okay, I will tell you in this lecture later that what is reversible and what is irreversible process, but definitely this process is irreversible process. Okay, and all we know that this in any irreversible process the entropy of the system always increases. Okay, so if I want to calculate that entropy, I would use some equation which I have written here, that is S is equals to n kb 5 by 2 minus log n lambda thermal to the cube, but I will tell you about this equation somewhat later. Okay, now now let us consider the case 2. Okay, you have understand the case 1 where the molecules on the, or all same of a same gas are contained only in the left portion. Okay, when you remove this partition, whole of this gas is spreads and acquires the whole volume of the container. Okay, this is a Joule expansion. Certainly it's an irreversible process and hence there is a net increase in entropy. Okay, that we will see later what is the increase in entropy. Okay, now consider the second case. Now in this case is different than this previous case. Okay, how it is different? That here in the case 1 we have taken a gas of only one kind of molecules. Okay, now what we are taking, we have two kinds of molecules. I have shown here with the red circles and with the green circles. Okay, so in left half of this container you have some different gas, and in right half you have a different gas. Okay, these two gases are not same. Okay, again you remove this partition. Okay, what happens? What happens is that this green molecules will spread throughout the volume, and so the red will also occupy the whole volume. Okay, now again this is, since this is a Joule expansion and you cannot by any process recover this original state by inserting a partition over here. If you want to again put that partition here, then you will never be able to attain the same state as it was before the partition was removed. Okay, it is not possible that if you put partition again and all the red will go to the left half and all the right will go to the right half. It is not possible. So, it is an irreversible process, and so again we know that in irreversible process the entropy of the system increases. So, again we will see that what is the actual expression for that, but it is sure that whatever increase in entropy appears here will also be equally that will be also for this red and for this green. Okay, so the total entropy change in this case 2 will be the double of this change that is in case 1. Okay. Now, let us see the case 3, which is entirely different from the previous two cases. How it is different? Again you can see that there is a partition, but now in left and in right both portion contains the same identical indistinguishable molecules on both sides. Okay. So, again they are allowed to go through the Joule expansion, that is I remove this partition, and again these molecules, the left hand side spreads over the whole volume and the right side molecules also spreads to the whole volume of the container. And if on the same analogy we want to discuss the case 3, then we will say that okay, if whatever the amount of entropy increases here should also appear here, that amount of change should also appear here. But you know that this case 3 is entirely different from the case 2, in the sense that here it is the same type of molecules on both sides of the partition. Okay. So, whatever state was before this partition, before the partition was removed, I can restore the same state. Okay. Suppose I remove this partition, okay, or the whole molecules of this left side and right side mix up together. If I again want to put the partition in the same position, then this state and this state would no longer be different from each other, because all molecules are identical, all molecules are same, identical, indistinguishable. So, this process is reversible process, unlike the two previous cases where the expansion was irreversible. So, this process is case 3 is a reversible process, and as you know that in reversible process the net change in entropy is 0. Okay. So, now comes the question of paradox. Okay. As you can see that in case 2 the red molecules gain some amount of entropy, and similarly green also gains some amount of entropy, and the sum of two entropies is the net change in entropy. Okay. So, here also one can demand that we should get some amount of change in entropy from the left portion and also from the from the right portion. So, we should have something delta S we should get, which should not be equal to 0. So, this is clearly a paradox. Okay. That we know that this is a reversible process, and in reversible process the change in entropy is 0, and if you take the analogy of this case 2, then it demands that there should be a change in entropy. Okay. So, let us take some mathematical aspects of this expansion, that what is actually the change in entropy happening in all these three cases. Okay. So, this change in entropy can be calculated through a equation which we call as Sackur-Tetrode equation. Okay. This is given by S equals to n kb within bracket 5 by 2 minus natural log of n lambda thermal to the power 3. Okay. Now, let me tell you the meaning of this equation. Actually, this equation, Sackur-Tetrode equation, gives you an expression of calculating the entropy of a monoatomic classical ideal gas which comprises of n atoms and at any temperature T, which is contained in this lambda thermal. This lambda thermal is called thermal wavelength, is called thermal wavelength given by h upon square root of 2 pi m kBT. Okay, and this little n is simply the number density, that is, it is the total number n divided by the total volume. Okay, so it's called number density or some concentration. Okay, so the important thing is that this Sackur-Tetrode equation is derived on the consideration that it takes into account the very fact of indistinguishability, Okay, this Sackur-Tetrode equation is derived or the entropy expression of this entropy is derived using quantum partition function, which takes into account the indistinguishability. Okay, you can see here that in this quantum partition function you have a factor of 1 over factorial n. So where does this factorial n comes from? Actually, this factorial n comes from the indistinguishable nature of molecules. Okay, so what is indistinguishability is I can tell you in very brief that if you want to if you have some configuration, okay, in which there are some atoms distributed in different energy states, okay, and if you exchange any two molecules or atoms, then if these are indistinguishable, then you won't get any new microstate or you won't get any change in the energy of the system. This is what indistinguishability in this context means. Okay, so out of all possible permutations which are counted factorial n times must be divided while taking indistinguishability into consideration. Okay, so if I want to calculate the change in entropy in the first case, then you can see here that delta S would be given by S final minus N initial, okay, because there is increase in this irreversible process. Okay, so I put there delta S final. What is little n for this this final? Little n, the number density will become half. Why it will become half? Because number of particle molecules are same, but the volume becomes double. So n upon V now becomes n upon 2V. So this number density n by 2, it becomes so this number density becomes half. Okay, so you put this so you use this Sackur-Tetrode equation and put here in delta S, you will get finally that delta S change in entropy is n kb log 2. It is simply n kb log 2. Kb is Boltzmann constant. Okay. Now, if you also want to calculate that what is delta S over kb, so that delta S over kb is n log 2. Now, remember that this delta S upon kb is related to the number of microstates available to this system now. Okay, remember from Boltzmann entropy relation S equals to kb log omega, you can see that this delta S upon kb is related to the number of microstates available to the system. So that is n log 2. Okay, so now what happens that is after Joule expansion, the microstates available to the system increases by this amount. Okay, n log 2. Okay, now here you can see in second case, so same amount n kb log 2 should come from red molecules and same amount n kb log 2 comes from this green molecules. So the total change in entropy should be twice n kb log 2, that is twice of the previous case. Okay, now again you can see the what are the number of microstates newly created. You can see that is now 2n log 2. Okay, now now why it is 0 in this case? This delta S 0 case can be explained. This, I mean, this paradox can be explained or it can be resolved just by taking into account the indistinguishability and the reversible process of this expansion itself. Okay. So, let me tell you that what is why we are saying that this is a reversible process. Okay. So, by reversible process I mean that the this a process which is infinitely slow, a process which is infinitely slow. Suppose suppose a system has is in some equilibrium state, okay, and then you do some changes in order to change its equilibrium state. So, the system acquires new equilibrium state. But if you do this process very slowly, infinitely slowly, then we can say that the system is undergoing very infinitesimal changes. That I can say that the system is not far away from its equilibrium, it is very near to its equilibrium, such that if I reverse the direction of process, then it will get its previous equilibrium state. Okay. Such is equilibrium states which are not far away from each other are called quasi equilibrium states, are called quasi static equilibrium state, and this process of infinitely slowly changing the equilibrium states is called quasi static equilibrium process. So, since this process is reversible process, then since it is a reversible process, since this is reversible process, so the entropy change should be 0. This you can understand it in another way through this mathematical equation also. See what happens. Initially there were suppose n molecules in the left portion, n molecules in the right portion. Okay. Suppose this volume was V, this volume was V. So, after this removal of this partition, now you have 2n molecules and 2V volume. 2n molecules is spread over 2V volume. So, what change do you see in this number density? This number density is n upon V. So, n now will become 2n and V now will become 2V. So, this will 2n upon 2V. So, there is no change in number density in this case, being because these molecules are indistinguishable from each other. Okay. So, so you see that you calculate the entropy in this case and then the entropy in this case, you will see that there is no change in this n. Okay. So, because this is a ratio of 2n upon 2V. So, mathematically you can also see by using this Sackur-Tetrode equation that delta S in fact is 0. So, by taking indistinguishability and the reversible process nature of this case 3, you can easily resolve this paradox or explain this paradox. Okay. So, I hope you have understand this Gibbs paradox. Okay. So, meet you in next video lecture. Thanks for your time. Thank you.